Good day, everyone. For today, we are the group to present about geothermal energy. I am Cindy Faustino, and I will discuss about what geothermal energy is. First of all, what is geothermal energy? Geothermal energy is a type of renewable energy within the Earth's interior. It comes from the Greek words geo, which means earth, and therme meaning heat. The reason why geothermal energy is referred to as a renewable energy source is because the water is replenished by rainfall and the heat is continuously produced by the earth. But where did geothermal energy come from? Well, it comes from the Earth's core, which is about 6,500 kilometers deep. The core is made up of an inner and an outer core, made up of very hot magma. The temperature in the magma remains very high due to the decay of radioactive particles. The mantle is made of magma and rock, and at some reasonable depths, the rocks and water absorb heat from this magma. These sites are characterized as geothermal resources. By digging wells and pumping the hot water to the surface, we make use of the geothermal energy. And as I've mentioned, we have geothermal resources. These are, by definition, hot water reservoirs that exist at various temperatures and that's beneath the Earth's surface. Thermal and compositional characteristics can be used to classify geothermal resources. And we have four classifications of it. The first one is the hydrothermal. These are known geothermal fields containing high temperature water in steam, mixture, or liquid phases. And it occurs naturally where magma comes close enough to the surface to heat the groundwater trapped in fractured or porous rocks, or where water circulates at great depth along faults. Hydrothermal resources are used for different energy purposes depending on their temperature or on how deep they are. The second one that we have is the geopressure. These resources contain hot liquid water at 150 degrees Celsius to 180 degrees Celsius at very high pressures up to 600 bar. The fluid in this deposit field reservoirs also contains methane and high levels of dissolved solids. The fluid is highly corrosive and thus very difficult to harvest and to handle. The third one is the magma. They are also called molten rock and typically contained under active volcanoes at temperatures above 650 degrees Celsius. And fourth, for the last one, is the enhanced or the dry rock geothermal system. They they are also called hot dry rock geothermal systems. These are not natural geothermal resources, and the idea is that water is injected into the hot rock formation at high pressure, and then the resulting hot steam is brought back to the surface. The system involves drilling of injection and production wells to a depth of 3 to 5 kilometers. The temperature of the hot rock in this depth can be around 250 degrees Celsius. Only the hydrothermal resources are currently being utilized out of the four geothermal resources categories. The other three are thought to have significant energy potential, but present technology make it impossible to produce from them. The next one is, how does geothermal power plants work? For this, wells drilled 1 or 2 miles down into the earth are used to pump steam or hot water to the surface at a geothermal power plant. And because these are the sites where the earth is very close or very hot close beneath the surface, you are more likely to locate one of these power plants in an area with a lot of hot springs, geysers, or volcanic activity. And the first one in the process is hot water is pumped from deep underground through a well under high pressure. And when the water reaches the surface, here, the pressure is dropped, which causes the water to turn into the steam. And then the steam spins a turbine, which is connected to a generator that produces the electricity. And the rotational energy from the turning turbine shaft is used directly to spin magnets inside a large coil and create electrical current. The turbine and the generator are the primary pieces of equipment used to convert geothermal energy to electrical energy. And then the steam cools off in a cooling tower here and then condenses back to the water. And then the cold water is pumped back into the earth through injection well to begin the process again. And then the cycle continues. So now that we know about how geothermal power plants work, let's talk about its types. The types of geothermal power plants are the dry steam power plant, binary cycle power plant, and the flash steam power plant. Let's tackle more about the dry steam plants. Dry steam plants use hydrothermal fluids that are primarily steam. Dry steam power plant systems were the first type of geothermal power generation plants built. They were first used at Dardareggio in Italy in 1904. And in this type, the steam travels directly to a turbine, which drives a generator that produces electricity. And the steam eliminates the need to burn the fossil fuels to run the turbine. And these plants emit only excess steam and very minor amount of gases. The next that we have here is the binary cycle power plant. Binary cycle power plant, in this type, the water or the steam from the geothermal reservoir never comes in contact with the turbine or with the generator units. Though to moderately heated, geothermal fluid and a secondary, hence binary, fluid with a much lower boiling point that water passed through a heat exchanger. And heat from the geothermal fluid causes the secondary fluid to flash to vapor, which then drives the turbine and subsequently the generators. And lastly, the third type is the flash steam power plant. These are the most common type of geothermal power generation plants in operation today. And fluid at temperatures greater than 360 degrees Fahrenheit or 182 degrees Celsius is pumped under high pressure into a tank at the surface held at a much lower pressure, causing some of the fluid to rapidly vaporize or flash. And then the vapor then drives a turbine, which drives a generator. And if any liquid remains in the tank, it can be flashed again in a second tank to extract even more energy. After the types, we now have the geothermal applications. Electricity generation, space cooling, and heating, cogeneration, and geothermal heat pumps are all solutions for utilizing the thermal energy supplied by geothermal energy systems. And geothermal energy was used by ancient people for heating and bathing. Because of the possible health advantages of minerals in hot geothermal water, hot springs are still used for bathing in many places of the world. And to further elaborate, the first application, which is the electricity generation. Geothermal energy is most commonly used for baseload electric power generation. Geothermal power plants can produce electricity as cheaply as some conventional power plants, and it costs 4.5 to 7 cents per kilowatt hour to produce electricity from hydrothermal systems. In comparison, new coal-fired plants produce electricity at about 4 cents per kilowatt hour. Initial construction costs for geothermal power plants are high because geothermal wells and power plants must be constructed at the same time. But the cost of producing the electricity over time is lower because the price and availability of the fuel is stable and predictable. The fuel does not have to be imported or transported to the power plant. The next application is about the space heating and space cooling. When we say space heating, it is space heating with geothermal energy is one of the most common widespread direct uses of geothermal resources. Space heating is also one of the oldest direct uses of geothermal energy. Third that we have here is the cogeneration. A cogeneration system utilizing geothermal energy and producing electricity and heat and or cooling represents an enhanced use of a resource. This is a cascaded application in which the used geothermal water leaving the power plant is used for heating or cooling before being re-injected back into the ground. Geothermal brine is re-injected at much lower temperatures in cogeneration applications in comparison to single power production. Lastly, we have geothermal heat pumps. Geothermal heat pumps use the constant temperatures near the surface of the earth to heat and cool buildings. It also transfers heat from the ground or water into buildings during winter and reverse the process during the summer. They use much less energy than conventional heating systems since they draw heat from the ground. It is also efficient when cooling your home and it can help you save energy and money. And aside from that, it can also help to lessen the air pollution. We already discussed about the applications of geothermal energy, and now let's tackle about what is geothermal heating. Geothermal heating is the use of geothermal energy to heat individual and commercial buildings, as well as for industry, through a distribution network. And in many places of the world, low-cost geothermal heat effectively heats a number of residential and business districts in the winter. China, Sweden, Iceland, Turkey, and the United States have some of the largest district heating systems. In Iceland, a small country, geothermal heat is used to heat about 90% of houses in the winter. Geothermal heat is used for space heating, mostly in a district heating scheme. And normally, hot geothermal water is not directly circulated to the district due to its undesirable chemical composition and characteristics of geothermal brine. Because of this, there is a need for heat exchangers. And what are heat exchangers? Heat exchangers are used to transfer the heat of geothermal water to fresh water, and this heated fresh water is sent to the district. This heat is supplied to the buildings through individual heat exchangers, and the heat exchanger is a system of pipes called a loop, which is buried in the shallow ground near the building. A fluid circulates through the pipes to absorb or relinquish heat within the ground. And now, how geothermal district heating works. From this, heat requirements and underground resources must be measured before a project can begin. The project has been designed and an administrative permit has been requested after the feasibility study and financial analysis of this matter have been completed. Two holes are required for geothermal district heating. One is for the injection well and the other one is for the production well. A production well is drilled into an underground aquifer and geothermal fluid flows up to the surface through a production pump, where it is transferred to a heat exchanger, where it is transferred to a new solution. This heat is then distributed through a heat-cold distribution network, which provides heating or cooling to specific applications. Meanwhile, the cool geothermal brine can return underground through the injection well, where it is reheated by the earth and then the cycle continues. And switching to this renewable resource reduces the need to import and burn fossil fuels, reducing carbon emissions and making our towns and cities cleaner and healthier. And geothermal heating can also provide stable, sustainable, secure, renewable, and carbon neutral cooling and hot water to homes, businesses, and manufacturers. When the district is heated by geothermal water, the rate of geothermal heat supplied to the district is determined from this equation. Q sub heat useful is equal to M times C sub P times the quantity T sub supply minus T sub return. where M is the mass flow rate of the geothermal water, C sub P is the specific heat of the geothermal water, T sub supply is the supply temperature, T sub return is the return temperature, and the Q sub heat useful is the rate of the geothermal heat that is being supplied. And assuming that this heat represents the average rate of heat supplied to the district, the amount of energy supplied for a specified period of time is determined from this equation. Energy consumption is equal to the Q sub heat useful times the operating hour divided by the efficiency of the heater, wherein the efficiency of the heater is the efficiency of the heating equipment. And once the amount of the energy consumption is now available, the corresponding cost of this energy can be determined using this equation. Energy cost is equal to the energy consumption multiplied by the unit price of energy. Let us have some examples. Example number 1. A residential district is currently heated by natural gas heaters in winter with an average efficiency of 85%. The price of natural gas is $1.30 per term. It is proposed to heat this district by geothermal water. On an average winter day, hot geothermal water is supplied to the district at 200 degrees Fahrenheit at a rate of 55 pound mass per second and returns at 130 degrees Fahrenheit after giving its heat to the district. How much revenue can be generated per year if the winter period can be taken to be equivalent to 2,800 hours of these average conditions? And geothermal heat is sold at a discount of 25% with respect to natural gas. For the solution to this example, using the specific heat of water at room temperature, which is equal to 1 British thermal unit per pound mass degrees Fahrenheit, we can get the rate of the geothermal heat supplied to the district using the formula. This one, the Q sub heat useful is equal to MCP times the quantity T supply minus T sub return. And then, by direct substitution of the values, we can obtain the useful heat equals to the 3,850 British thermal unit per second. Taking note that natural gas heaters have an efficiency of 85%, the corresponding consumption of natural gas during a winter period of 2,800 each is, using this formula, the natural gas consumption is equal to the useful heat times the operating hours over the efficiency of the heater. And then by direct substitution of the given values, we can obtain a natural gas consumption value of 4.566 times 10 raised to 5 of term per year. And if the geothermal heat is sold at a discount of 25%, the potential revenue that can be generated by selling geothermal heat can be obtained using this formula. Potential revenue is equal to the quantity of 1 minus the discount times the natural gas consumption times the unit price of the natural gas. And then substituting again the values, we can obtain the potential revenue amounting to $445,150 per year. And that's the example for that. And the next that I will introduce to you is the degree day method, which can be used to find the annual energy consumption of a building. By definition, it is the simplest and most intuitive way of estimating the annual energy consumption of a building is the degree day or degree hour method. which is a steady state approach. This method can be used for geothermal heating systems as well as solar, biomass, and other fossil fuel-based systems. The degree day method is also used to calculate cooling energy consumption during the summer. Here is a figure, and based from this figure, the heater of a building will not turn on as long as the internal heat gain makes up for the heat loss from a building. And you may think that anytime the outer temperature drops below the indoor temperature at which thermostat is set, the heater will turn on to make up for the heat losses to the outside. However, the internal heat generated by people, the lights, the appliances in occupied buildings, as well as the heat gain from the sun during the day, will be sufficient enough to compensate for the heat losses from the building until the outdoor temperature drops below a certain value. And the outdoor temperature above which no heating is required is called the balance point temperature. And it is determined using this equation, where K overall is the overall heat transfer coefficient, T sub I is the indoor temperature, T sub balance is the balance point temperature, and the Q sub gain is the heat gain. The rate of energy consumption of the heating system can be determined using this formula, where N sub heater is the efficiency of the heating system, K sub overall is the overall heat transfer coefficient, T sub O is the outdoor temperature, T sub balance is the balance point temperature, Q sub heating is the rate of energy consumption of the heating system. The number of degree days for a heating season is determined using this formula. Degree wherein the DD subheating is the heating degree days. T sub OAVG day is the average outdoor temperature for each day, and T sub balance is the balance point temperature. And please take note that the positive sign exponent indicates that only positive values are to be counted, and the temperature difference is to be taken 0 when the outdoor temperature is greater than the balance point temperature. Let's have some examples. For a given day, we have the highest outdoor temperature of 50 degrees Fahrenheit, lowest outdoor temperature of 30 degrees Fahrenheit, average outdoor temperature of 40 degrees Fahrenheit, and the degree days for that day for a balance point temperature of 65 degrees Fahrenheit. Using the formula, we just need to substitute all the given values here, direct substitution, and we can obtain 25 degrees Fahrenheit per day, degree day. And if you will convert it into a degree hour, you will have 600 degrees Fahrenheit per hour. And take note that the number of degree hours is equal to 24 times the number of the degree days. When heating degree days are available for a given location, the amount of energy consumption for the entire winter season can be determined using this formula. Energy consumption is equal to the overall coefficient all over the efficiency of the equipment multiplied by the degree day heating. And the amount of fuel consumption corresponding to this energy consumption can be determined by using heating value of the fuel as this fuel consumption is equal to the energy consumption all over the heating value of the fuel. And if ever the heating is accomplished by a heat pump, heater needs to be replaced by heating COP, or the coefficient of performance of the heat pump. Also, in this case, energy is consumed in the form of electricity. That is, by using this formula, electricity consumption is equal to the overall coefficient all over the coefficient of performance of heating multiplied by the degree day of heating. And if we are to calculate the cooling energy consumption, we need to use the cooling degree days and the cooling coefficient of performance of the air conditioner by using this formula. Electricity consumption is equal to the overall coefficient divided by the cooling coefficient of performance multiplied by the degree day of cooling. And lastly, in above equations, the overall heat loss coefficient of the building can be determined from the winter design temperatures and design heating load of the building using this formula. In here, in this formula, outdoor temperature is the design temperature of the location, and it represents a selected minimum winter temperature at which the heating equipment can provide an adequate heat to the building so that the indoors can be maintained at the comfort temperature. And this is the table of the average winter temperatures and number of degree days for selected cities in the United States according to ASHRAE 2020, 2008. And despite the simplicity, accurate results can be obtained using the degree day method for most houses and single zone buildings. Besides, it characterizes the severity of the weather at a location accurately, and it also serves as a valuable tool for gaining an intuitive understanding of annual energy consumption. So because of that, let's have an example for annual energy consumptions for different heating systems. Example number 3. Consider a house with an overall heat loss coefficient of 0.5 kilowatt per degree Celsius and a heating degree days of 2,500 degrees Celsius per days. Determine the annual heating energy consumptions for the following heating systems. A coal heater with efficiency of 0.75 and heating value of coal is equal to 30,000 kilojoules per kilogram. B is for natural gas heater with efficiency of 0.85. C using a heat pump with COP of 2.5. D using a resistance heater with an efficiency of 1. And lastly, geothermal with an efficiency of 1. So for the solution, to find the annual heating energy consumption for coal heater, we may use the formula of energy consumption is equal to the overall heat loss coefficient divided by the efficiency of the heating system multiplied by the degree day heating. And then by direct substitution of the values, we can obtain that the amount of energy consumed as equal to 1.44 times 10 raised to 8 kilojoules. And to find the value for the coal consumption, we can use the formula for fuel consumption, which is the coal consumption is equal to energy consumption divided by the heating value of the fuel, and then substitute the value that we obtained earlier, 1.44 times 10 raised to 8 kilojoules divided by the 30,000 kilojoules per kilogram. And we now have 4,800 kilograms value for the coal consumption. The next one is for the natural gas heater with an efficiency of 0.85. Same procedure as we have with the coal heater, we can use the formula for the energy consumption. Then just plug in all the values, all the given values. And after that, we can obtain the energy consumption is equal to 1,204 therms. For the third one, it is using a heat pump with a coefficient of performance is equal to 2.5. And since we are using a heat pump, the formula that we are going to use will be the formula for electricity consumption, wherein electricity consumption is equal to the overall heat loss coefficient all over the coefficient of performance times the degree day of heating. And then substitute all the values and we will get the 12,000 kilowatt hour as the electricity consumption using heat pump with a coefficient of performance equal to 2.5. Fourth one, using a resistance heater with an efficiency equal to 1. Same procedure with the heat pump. We will make use of the formula for electricity consumption as well, but we need to replace the COP with the efficiency of the heating system. But still it is multiplied by the degree day heating. And then substitute the given values here and we will obtain the value of electricity consumption equal to 30,000 kilowatt hour. And lastly, for the geothermal heater, we can make use of the formula for energy consumption in winter season, which is the energy consumption is equal to the overall heat loss coefficient divided by the efficiency of the system multiplied by the degree day heating, and then substitute all the given values and we will get 108,000 megajoules or 30,000 kilowatts. And that is how we solve for the annual energy consumptions with different heating systems. And for cost comparison, the cost of energy for each system can be obtained by multiplying energy consumption by the unit price of energy. And that's all for the general heating topic under the geothermal energy.
Good morning, everyone. My name is Angelica, and I will continue to tackle Topic 7.4, Geothermal Cooling, and Topic 7.5, Geothermal Heat Systems. So let's proceed. So geothermal systems are home heating and cooling systems that gather heat from the earth. Geothermal heat pumps, GHPs, use the relatively constant temperature of subsurface soil as the exchange medium. Absorption cooling system. Cooling using absorption is similar to traditional vapor compression, except that the compressor is replaced by a chemical cycle taking place between an absorber, a pump, and a regenerator. Simply put, cooling dissolves a vapor in a liquid, which is the absorbent, pumps the solution to a higher pressure in the regenerator, and then uses heat to evaporate the refrigerant vapor out of the solution. Next slide would be absorption refrigeration. Absorption refrigeration is a form of system that is economically attractive when there is a source of inexpensive thermal energy at a temperature of 100 to 200 degrees Celsius. Absorption refrigeration systems involve the absorption of a refrigerant by a transport medium. As a reference, inexpensive thermal energy sources include geothermal energy, solar energy, and waste heat from cogeneration or passive steam plants, and even natural gas when it is available at relatively low price. So there are three absorption refrigeration systems. The ammonia water system, which is most widely used and will be discussed later as an example. The water lithium bromide, and the water lithium chloride system. So the latter two system, which is the water lithium bromide system and the water lithium chloride system, are limited to applications such as air conditioning, where the minimum temperature is above the freezing point of water. In this system, water serves as the refrigerant. Next slide. We have here an illustration of ammonia water refrigeration. Let's have a brief history. The ammonia water refrigeration machine was patented by the Frenchman Ferdinand Carré in 1859. So within a few years, the machines based on this principle were being built in the United States, primarily to make ice and store food. So the output of cold air is the result of the process of removing heat from the circulated air, transferring that heat to the ground, and returning cool air back. So, an absorption system consists of four main components, namely the generator here, the generator, the condenser, the evaporator, and lastly the absorber. So, and so let's dissect this diagram. We'll start here, the evaporator, right here. Let's start in the evaporator. So ammonia vapor leaves the evaporator and enters the absorber here, where it dissolves and reacts with water to form ammonia water. This is an exothermic reaction, thus heat is released during this process. The amount of ammonia that can be dissolved in water is inversely proportional to the temperature. It means we need to maintain low temperature in the absorber to maximize the amount of ammonia dissolved in water. That's why there is cooling water that's being feeded here. The liquid ammonia water solution, which has strong ammonia, is then pumped to the generator here. Pumped to the generator, going to the generator. Heat is transferred to the solution from a source. From here, for example, geothermal heat or solar energy from external source to vaporize some of the solution. Inside the generator here, the vaporized solution is filtered by an analyzer wherein by the time that the ammonia water vapor reach the analyzer, the water vapor will get filtered back to the generator. Mm. After that, when it gets filtered back to the generator, it will then go back to the absorber again. Mm. Uh, Absorber again, leaving the vapor, which is rich in ammonia, goes to the rectifier because the water vapor goes back in the generator and to the absorber. So the pure or the mixture which is high in ammonia goes to the next stage, which is the rectifier. The rectifier separates the remaining water through the exchange of heat and returns it to the generator back to the absorber again. So right here, it filters again the remaining water vapor and liquidify it and go and put it back to the generator and then put it back to the absorber. So the hot ammonia water solution, which is rich in ammonia, then passes through a regenerator here because the pure ammonia gets to pass through the rectifier. This mixture is composed of weak ammonia, has only small amount of ammonia mixture. So it passes through the regenerator where it transfers some heat to the rich solution, uh, leaving the pump and is throttled to the absorber pressure because by increasing the regenerator temperature, the vapor pressure of the refrigerant is increased, and therefore separation of the refrigerant from the solution occurs. So there is an obstruction of solubility here at the regenerator, which reprimands the absorber supply of the solution to the generator. So going back to the high pressure pure ammonia, which gets through the rectifier here. This has become partially liquidified because of the exchange of heat applied in the rectifier. So it will then reach the condenser. After passing the connecting pipe in which the condenser absorbs the remaining heat and then convert the partial liquid ammonia into liquid. So the high pressure liquid ammonia then enters the expansion valve right here, where the pressure between the molecules decreases, resulting to the temperature to decrease too. Therefore, we'll have an output of a low pressure, low temperature liquid ammonia, and it will eventually start the cycle again when it was feeded to the evaporator. And it will go to the absorber, to the pump, to the regenerator, generator, rectifier, condenser, and then goes back again. So, next slide. So, comparison of vapor absorption system and vapor compression system. So, vapor absorption system uses heat energy, low grade, to change the condition of the refrigerant from the evaporator, often classified as heat-driven systems, while vapor compression systems uses mechanical energy, high grade, to change the condition of refrigerant from the evaporator. Second, the moving part of the system is a pump. Thus, the operation of this system is essentially quiet and is subjected to little wear. So that's for vapor absorption system. Then the system with same capacity has more wear, tear, and noise due to the moving parts of the compressor. And then vapor absorption system, the load variation do not affect the performance of a system. While in vapor compression system, the performance is adversely affected in part loads. And then the refrigerant leaving the evaporator has no bad effect on the system for vapor absorption system. And then it is essential to superheat the refrigerant leaving the evaporator for vapor compression system. So vapor absorption system has low COP or the coefficient of performance, while vapor compression system has high coefficient of performance. So number of components are more, that it is bulky for vapor absorption system, and less number of components that it is less bulky for vapor compression system. And lastly, vapor absorption system refrigerant charging is difficult, while refrigerant charging is simple in vapor compression system. Therefore, we can conclude that absorption refrigeration systems should be considered only when the unit cost of thermal energy is low or a free renewable energy source, such as geothermal energy, is available. An ideal use of an absorption system is when it uses the waste heat of a power plant, such as geothermal in a cogeneration scheme. Absorption refrigeration systems are primarily used in large commercial and industrial installations. Next slide is so right here is an absorption chiller. So air conditioning system based on absorption refrigeration called absorption chillers. This is what it looks like. It performs best when the heat source can supply heat at a high temperature with little temperature drop. The absorption chillers are typically rated at an input temperature of 116 degrees Celsius or 240 degrees Fahrenheit. The chillers perform at lower temperatures, but their cooling capacity decreases sharply with decreasing source temperature, about 12.5% for each 6 degrees Celsius, 10 degrees Fahrenheit drop in the source temperature. Therefore, the economic aspects must be evaluated carefully before any absorption refrigeration system is considered, especially when the source temperature is below 93 degrees Celsius, because you'll get in trouble when the source temperature will decrease. So here is the coefficient of performance of absorption refrigeration systems. So coefficient of performance absorption of absorption refrigeration system is equal to the rate of cooling over rate of the generator plus the input work input work of the pump. So equivalent to rate of cooling and rate of generation system. Next is we have here an example problem for potential revenue from a geothermal cool system. So let me read it. So geothermal liquid water from a well is available at 95 degrees Celsius at a rate of 150,000 kilograms per hour and is to be used for space cooling using an absorption cooling system. Geothermal water leads the generator of the absorption system at 80 degrees Celsius. If the coefficient of performance of the absorption system is 0.65, determine the rate of cooling provided by the system. This geothermal cooling system is replacing a conventional vapor compression refrigeration system with an average of COP value of 2.5, and the unit price of electricity is $0.125 per kilowatt hour. Determine the annual potential revenue that can be generated by this geothermal cooling system if geothermal cooling is sold with a discount of 10% compared to conventional cooling. Use a seasonal cooling period of 1,750 hour at the calculated cooling rate. So here is the solution. So the specific heat of water at room temperature is 4.18 kilojoules per kilogram degrees Celsius. The rate of heat transfer in the generator of the absorption system is calculated as 9.405 times 10 raised to 6 kilojoules per hour. So it was calculated by by substituting the formulas in this substituting the values in this formula. So next is using the definition of the COP of an absorption cooling system. The rate of cooling is determined to be 1,698 kilowatts um, by multiplying the coefficient of performance of the absorption cooling system and the rate of cooling here. So 0.65 times 9.405 times 10 raised to 6 kilojoules per hour, which was calculated here. So we get 1,698 kilowatts. Next is if a conventional cooling system with a COP of 2.5 is used for this cooling, the power input would be, so to get the power input, we need to divide the rate of cooling system to the coefficient of performance. So by substituting the values 1,698 kilowatts over 2.5 is equal to 679.3 kilowatts. Next is the electricity consumption for a period of 1,750 hours is electricity consumption is equal to work input times operating hours equal to 679.3 kilowatts times 1,750 hours is equal to 1.189 times 10 raised to 6 kilowatt hour. Next is at a discount of 10%, the revenue generated by selling the geothermal cooling is we get the revenue by this formula. So 1 minus the percent discount times the electricity consumption times unit price of electricity. So here we go, 1 minus 0.1 times 1.189 times 10 raised to 6 kilowatt hour times $0.125 per kilowatt hour. Then we get this $133,800. So next, we'll go to chapter 7.5 geothermal heat pump systems. So heat pumps are generally more expensive to purchase and install than other heating systems, but they save money in the long run in some areas because they lower the heating bills. Despite their relatively higher initial cost, the popularity of heat pumps is increasing. So it's like you'll invest right away and pay high initial costs, then gradually paying smaller bills but will eventually be higher who knows, than the initial cost of installing heat pump technologies. But of course, we're talking about in the long run here. So the COP, or coefficient of performance of a heat pump in the heating mode, is defined as the heating effect divided by the work input. And the coefficient of performance of the heat pump in the cooling mode, called air conditioner, is defined as the cooling effect divided by the work input. So proceeding here, heat pump operation. So heat pumps and air conditioners have the same mechanical components. Therefore, it is not economical to have two separate systems to meet the heating and cooling requirements of a building. One system can be used as a heat pump in winter and an air conditioner in summer, and it is just referred to as a heat pump. This is accomplished by adding a reversing valve to the cycle as shown in the image here and here. As a result of this modification, the condenser of the heat pump located indoors functions as evaporator of the air conditioner in summer. Here, in summer, we need the cooling mode. And then also the evaporator of the heat pump located outdoors serves as the condenser of the air conditioner. So here. This feature increases the competitiveness of the heat pump. Such dual-purpose units are commonly used in apartment units and motels. So, most competitive in areas that have a large cooling load during the cooling season and a relatively small heating load during the heating season. So, least competitive in areas where the heating load is very large and the cooling load is small. So, it prefers the cooling load, right? Right. Next slide is so types of heat pumps. So first we have geothermal or ground source heat pumps. So represent the most common use of geothermal energy in terms of numbers of units installed. These heat pumps are called geothermal heat pumps as they utilize the heat of the earth. They require long tubing placed deep in the ground where the soil temperature is relatively constant. So ground source heat pumps provide higher values of coefficient of performance compared to air source units. The ground at a few meters deep is at a higher temperature than the ambient air in the winter, and it is at a low temperature than the ambient in summer. So this system uses higher ground temperatures in winter for heat absorption, heating mode, and cooler ground temperatures in summer for heat rejection cooling mode. And this is the reason for higher COPs. So supplementary heating may not be required, but heat pump system must be large enough to meet the maximum heating load. Next, we have here the diagram. In the heating mode operation of a ground source heat pump, heat is absorbed from the ground at TL, or the low temperature, which is higher than the temperature of the ambient air. So heat is supplied to the indoors or uh, indoors at pH or the high temperature by the heat pump. In the cooling mode, uh, heat is absorbed from the indoors at TL or the low temperature and rejected to the ground at high temperature, which is at a lower temperature compared to the temperature of the ambient air. Next, oh wait, um, next is the atmospheric air to air systems. So the major problem with air source systems is frosting, which occurs in humid climates when the temperature falls below 2 to 5 degrees Celsius. The frost accumulation on the evaporator coils is highly undesirable since it seriously disrupts heat transfer. The coils can be defrosted though, however, by reversing the heat pump cycle, running it as an air conditioner. This results in a reduction in the efficiency of the system. So it also require a supplementary heating system such as electric resistance heaters or an oil or gas furnace. Next is the water source system. So usually use well water from depths of up to 80 meter in the temperature range of 5 to 18 degrees Celsius, and they do not have a frosting problem. They typically have higher COPs but are more complex and require easy access to a large body of water such as underground water. So supplementary heating may not be required here too, but heat pump system must be large enough to meet the maximum heating load. So only the atmospheric air-to-air systems require a supplementary heating system such as electric resistance heaters or an oil or gas furnace. Next is comparison of performance of an air source heat pump and a ground source heat pump with the following data in winter operation. So ground source heat pump, lower temperature is 10 degrees Celsius, high temperature is the at 25 degrees Celsius. While an air source heat pump, the lower temperature is 0 degrees Celsius and the high temperature is 25 degrees Celsius. So actual COP of ground source heat pumps ranges between about 3 and 5. Actual COP of air source heat pumps ranges between 1.5 and 3. So here is the formula for COP. Okay, so high temperature all over high temperature minus low temperature. So we get here 11.9 and we get 19.9 here at ground source heat pump. Next is classification of ground source heat pumps according to the configuration of piping and heat source. So first is horizontal loop heat pump. So it involves horizontal underground piping in 1.2 to 2 meter depth. It is suitable when there is sufficient area for pipe burial, such as the relatively large backyard of a house. So as you can see here, it needs a lot uh it needs a lot of area because it was laid horizontally. And next, second is vertical loop heat pump. It is also called borehole loop heat pump. Vertical piping in 10 to 250 meter depth is used. It can be installed everywhere as a small field following vertical drilling is sufficient. This type of heat pump is selected for meeting heating and cooling requirements of a medium-sized university campus with several buildings. Vertical piping is more expensive than horizontal piping for a given heat transfer surface area. These systems require virtually no regular maintenance and they are safe. However, the capacity is limited for borehole and the ground temperature is relatively low. Next, we have the groundwater well heat pump. So there is a groundwater right here. So underground water is circulated through the evaporator of the heat pump unit. Heat is transferred from the water to the refrigerant flowing in the evaporator. The cooler water leaving the evaporator is dumped back to the ground um, at a different location. So the water well is located in 5 to 50-meter depth. These systems can provide high capacities with relatively low cost. The temperature of water is relatively high as compared to horizontal loop and borehole heat pumps. An aquifer is needed for sufficient water yield. The wells need to be maintained and water quality should be monitored too. So it requires a lot of maintenance here. Next is the classification according to fluid type circulating in the evaporator and the condenser. So, water to air heat pump. If water is circulating through the evaporator and air is circulating through the condenser. Next is the water to water heat pump. If the heat pump is used to produce hot water by circulating water through the condenser and underground water is circulated in the evaporator. So next we have an example here again of an air source heat pump. So let me read. A house in Cleveland, Ohio is equipped with an air source heat pump system that is used for space heating in winter. The seasonal COP of the heat pump in winter is estimated to be 1.5. The design heating load of the house is calculated to be 19 kilowatts for an indoor temperature of 25 degrees Celsius. The unit cost of electricity is $0.12 per kilowatt hour. Determine the annual electricity consumption and its cost for this house. So the annual heating degree days of Cleveland, Ohio is 3,528 degrees Celsius per days. And the 97.5% winter design temperature of Cleveland is negative 15 degrees Celsius. So here's the solution. The annual heating degree days of Cleveland, Ohio is 3,528 degrees Celsius days. The 97.5% winter design temperature of Cleveland is negative 15 degrees Celsius. The overall heat loss coefficient of the house is determined from.
So we have here the Q design is equal to K overall times TI minus TO design. So from this formula, we get the K overall equal to Q design over TI minus TO design. So let's substitute the values. So 19 kilowatt over 25 minus negative 15 degrees Celsius, we get 0.475 kilowatt per degree Celsius. Next is here. Then the annual electricity consumption of the house for heating is determined to be electricity consumption is equal to overall K overall over the coefficient of performance times the day heating. So 0.475 kilowatt per degree Celsius over 1.5 times 3,528 degrees Celsius days. So we get 26,810 kilowatt hour. So the cost of this electricity consumption is heating cost equals electricity consumption times unit cost of electricity. So you multiply 26,813 kilowatt hour times $0.12 per kilowatt hour. Then we get $3,217. Next slide is another example for ground source heat pump. So reconsider example 7.4. If the house in Cleveland is heated in winter by a ground source heat pump, consider with a seasonal COP of 3.5, determine the annual electricity consumption and its cost for this house. If the house in Cleveland is heated in winter by a natural gas furnace that is 88% efficient, determine the annual natural gas consumption and its cost in winter. The unit cost of natural gas is $1.10 per term. So next, the annual electricity consumption of the house for heating is determined to be electricity consumption is equal to overall K of all over the COP times the days heating. So we have 0.475 kilowatt per degrees Celsius over 3.5 times 3,528 degrees Celsius days. So we get 11,490 kilowatt hour. So the cost of this electricity consumption is heating cost equals to electricity consumption times unit cost of electricity. We get $1,379 by multiplying 11,490 kilowatts to and $0.12 per kilowatt hour. Next is the annual natural gas consumption of the house for heating is determined to be gas consumption is equal to K overall over the furnace and then the days again. So 0.475 kilowatts over degrees per degrees Celsius over 0.88 times 3,528 degrees Celsius days. So these are calculated because of conversion. These are for conversions. And then we get the 1,559 terms. Next, the cost of this natural gas consumption is heating cost is equal to gas consumption times unit cost of natural gas. We get 1,559 terms times $1.10 per term. And then we'll have $1,715. So those are the formulas for those scenarios. Okay, so that would be it for my topic. Thank you.
Aloha! I am Veronica Vigilla, and I will discuss the geothermal power production. Let's start with a quick and brief history of geothermal power plant. The first and the oldest geothermal power plant in the world is in Larderello in Italy. Larderello Geothermal Power Plant was built in Italy year 1904 and was completed in 1913 with a capacity of 250 kilowatts. The Geysers is a geothermal field located in California's Mayacamas Mountains. It is one of the world's biggest single geothermal field comprising of 22 geothermal power plants with an installed capacity of 1,517 million watts. Additional information that you may need to know. In fact, about 14,300 million watts of geothermal electricity are produced in 24 countries as of 2018, and 28% of this generated in the United States with 3,550 million watts. Another interesting fact is that the Philippines is the third largest producer of geothermal electricity after the United States of America and Mexico. Now, let's talk about the main types of geothermal plant. There are three main types, namely direct steam, flash steam, and binary cycle power plant. First type of geothermal power plant is the direct steam or dry steam plants. Direct steam or dry steam plants are the most common types of geothermal power plants, accounting for about half of the installed geothermal plants. They work by piping hot steam from underground reservoir directly into the turbines from geothermal reservoir, which power the generators to provide electricity. And after powering the turbines, the steam condenses into water and is piped back into the earth via the injection well. Next type is the flash steam plants. It is different from dry steam because they pump hot water rather than steam directly to the surface. These flash steam plants pump hot water at a high pressure from below the earth into a flash tank on the surface. The flash tank is at much lower temperature, causing the fluid to quickly flash into steam. The steam produced powers the turbines. The steam is cooled and condenses into water where it is pumped back into the ground through the injection well. There are two types under flash geothermal power plant. First is the single flash plant. In a single flash plant, the pressure of geothermal water is trapped to a predetermined value in a flash chamber. The resulting two-phase mixture is separated into liquid and vapor in the separator. The vapor is routed to turbine in which it expanded to condenser pressure. Steam exciting the turbine is condensed with cooling water obtained in a cooling tower or a spray pan before being re-injected. And the liquid geothermal water at state 6 and that in state 5 is re-injected back to the ground. Now, we can calculate the power output from the turbine by neglecting kinetic and potential energy changes. And it is determined by the difference between enthalpy multiplied by the mass flow rate of the geothermal water. We can also calculate the thermal efficiency of the plant by using these two formulas. Okay, another type of flash geothermal power plant is the double flash power plant. In a double flash geothermal power plant, the liquid water leaving the separator after the first flushing process is further expanded in a second flush chamber. Additional water vapor resulting from this process is separated and sent to a lower pressure stage of the turbine for additional power production. The rest of the operation is the same as the single flash plant. Thermodynamic analysis of double flash power plant is very similar to that of a single flash plant. In this configuration, power is produced from the turbine by the expansion of two fluid streams entering at state 3 and state 8, as you can see in the formula. Let's proceed to other types of geothermal plants. Other type is called the binary cycle power plant. In these binary cycle plants, the main difference is that the water steam from below the earth never comes in direct contact with the turbines. Instead, water from geothermal reservoir is pumped through a heat exchanger where it heats a second liquid, like isobutane, which boils at a lower temperature than water. The second liquid is heated into steam, which powers the turbines that drives the generator. The hot water from the earth is rejected into the earth through the injection well, and the second liquid is recycled through the turbine and back into the heat exchanger where it can be used again. Binary cycle plants use the geothermal brine from liquid-dominated resources at relatively low temperatures. There is another type of geothermal power plant, and it is combined flash or binary plant, also called hybrid plant, incorporates both a binary unit and a flashing unit to exploit the advantages associated with both systems. The liquid portion of the geothermal mixture serves as the input heat for the binary cycle, while the steam portion drives a steam turbine to produce power. Power is obtained from both the steam turbine and the binary turbine. The geothermal liquid water is re-injected to the ground at a lower temperature, which is the state 7, compared to a single flash plant. Thermal efficiency of combined flash binary geothermal power plant can be determined from this formula. Net output power divided to energy input, which is equivalent to power output from turbine minus 2 power output from pump minus 2 power output from fan divided to energy input. Now let's proceed to this diagram. It is the installed capacity of different types of geothermal plants in the world as of 2015. The most common geothermal plant type, according to this diagram, is the single flash, which account for more than 5,000 million watts of installations worldwide. This is followed by dry steam, double flash, and binary plants. Triple flash and combined flash or binary plants also exist, but in much smaller capacities. Now, let's try to solve a problem of what we have discussed a while ago. Example problem 1. A geothermal site contains geothermal water available at wellhead at a rate of 100 kg per second. The geothermal water is at 180 degrees Celsius with a vapor fraction of 20%. The ambient conditions are 25 degrees Celsius and 1 atmospheric pressure. Let's find what is the maximum thermal efficiency of geothermal power plant using this resource. What is the maximum amount of power that can be produced from the site? And lastly, if a typical second law efficiency for a geothermal power plant is 30%, predict the actual power output from a geothermal power plant at this rate and its thermal efficiency. So this is the solution for the problem 1, letter A. What is the maximum thermal efficiency of a geothermal power plant using this resource? The maximum thermal efficiency can be determined from the Carnot efficiency relation using the geothermal source. In our problem is 180 degrees Celsius in ambient or the dead state temperatures with 25 degrees Celsius. We need to convert it to Kelvin, so add 273. And we will get 34.2% as the maximum thermal efficiency of a geothermal power plant. Next, what is the maximum amount of power that can be produced from this site? The enthalpy and entropy values of geothermal water at the wellhead state and dead state are obtained from steam tables. And by following the formula, we will get 226,800 kilowatts as the maximum amount of power that can be produced from the site. Next, if a typical second law efficiency for a geothermal power plant is 30%, predict the actual power output from a geothermal power plant at its site and its thermal efficiency. The second law efficiency of power plant is defined as the actual power output divided by the maximum power output. It is also defined as the actual thermal efficiency divided by the maximum thermal efficiency. Then, for a second law efficiency of 30%, the actual power output and the actual thermal efficiency are predicted to be 8,040 kilowatts and 10.3%. Now, let's proceed to geothermal cogeneration. The meaning of cogeneration is that it is the production of more than one useful form of energy, such as process heat and electric power from the same energy resource. A cogeneration plant produces electricity and heat to your home. This is done by boiling water using renewable fuels such as peat, Christmas trees, and leftovers from forests and demolitions. The steam makes the turbine spin, which drives the generator. The produced electricity is then transported out to the power grid. The remaining heat warms up the district heating water, which is transported home to you via pipelines. With the help of a heat exchanger in your house, the water warms up your home and your tap water. When the district heating water has passed the heat exchanger, it is returned to the cogeneration plant to reheat. So one of the use of cogeneration is provide district heating, that is space, hot water, and process heating for residential and commercial buildings. Cogeneration systems can generally be arranged as tapping cycles and bottoming cycles. In tapping cycle, the fuel is burned or an energy source such as geothermal is utilized in a power cycle and power is generated first. The waste heat output from the power cycle is then used to produce a useful heat output in a boiler or heat exchanger. This scheme of cogeneration is most commonly used. It is particularly suitable when the electric demand of the facility is greater than the thermal demand and the process heat temperature requirements are not too high. In bottoming cycle, heat is produced first in a boiler or heat exchanger, and electricity is generated by using the waste heat of fluid stream leaving the process heat equipment and or the boiler. The scheme of cogeneration is less common than the tapping skill, and it is particularly suitable when the plant needs process heat at a high temperature. Next, let us know the advantages of cogeneration systems. These are some of it. First is the ability to improve the efficiency of fuel used in the production of electrical and thermal energy. Next, it leads to significant energy savings and corresponding environmental advantages. Other advantages is that cogeneration plants have proved to be economically very attractive. Next, a standard generator will only create one form of energy, which is the electricity. However, in cogeneration, there will be two forms of energy, which is electricity and heat. Now let's proceed to the formula that we can use in solving problems related to cogeneration. The efficiency of cogeneration plant is usually expressed by utilization factor. The utilization factor of cogeneration plant involving an electricity producing unit and absorbent cooling system may be expressed as this formula: net power output plus rate of cooling delivered divided to total rate of heat input. Similarly, the utilization factor of a cogeneration plant involving an electricity producing unit and heating system may be expressed as net power output plus rate of heating delivery divided to total rate of heat input. If a cogeneration plant provides electricity, heat, and cooling at the same time, or the trigeneration, the utilization factor may be expressed as this formula: net power output plus rate of heating delivered plus rate of cooling delivered divided to total rate of heat input. Next is the comparison of potential revenues from geothermal energy for various uses. The results show that using the same geothermal resources for a cogeneration application, which is the power plus heating, can provide potential revenues of $506,000 per year compared to $300,000 when it is used for power generation only. A cogeneration scheme involving power generation and absorption cooling can only provide potential revenue of $310,000, which is a little higher than that by a power generation system. However, the temperature of geothermal water at the exit of absorption cooling system is still high at 90 degrees Celsius, which makes it suitable for heating applications. Note that space heating cannot be added to the space cooling in this trigeneration scheme since no space heating is needed when space cooling is used in summer. And a potential solution is to operate the cogeneration system with power generation space heating in winter and with power generation space cooling in summer. When this is the case, the annual potential revenue becomes $300,000, the power plus $205,000 heating plus $110,000 cooling, which is equivalent to $616,000. Thank you, and that is all about geothermal energy.